maths in the wild, we shall be visiting an area of maths which produces, some might say, the most beautiful results, curves and surfaces. And for one of the first times on live TV, we can actually meet a surface in its natural habitat, University of Leicester. Autumn is a special season for the surface. Every year, around the time that Katrin teaches the Curves and Surfaces module, the surfaces give birth to the curves, and we're in a particularly fortunate situation that we can study them this year. There are two species of curves that are born, the plane curve and the space curve. Oh, look at this little cheeky plane curve here. So here we have a plane curve. Its name is derived from the fact that it exists on a 2D plane. The curve that we've managed to spot here usually is quite camera shy, so we're quite lucky today. And we'll just show you its properties.
The plane curve has a few properties that we can study, whether or not the curve is something called regular, its length, and also its curvature. Also, due to the fact that we can write the same looking curves in many ways, parameterizations, looking at these properties can help us build a picture of what our plane curve looks like.
To look at whether or not a plane curve is regular, we need to look at how fast the curve moves. In other words, its rate of change. We can differentiate this little fella here and see its rate of change, or how fast it moves, if you will. A plane curve is regular if the magnitude of its speed is not equal to 0, meaning that this curve deviates from straightness and has some wiggles that we can have a look at. In addition, we can also have a special type of curve that we call unit speed. This is a regular curve that has a speed of 1. For our little fella, it is regular when you restrict its domain, but it is not unit speed.
We can also look at how long a section of the curve is by integrating the norm of its speed. To do this though, our little fella needs to be regular. However, sometimes the curve finds it rude when you ask for its length and hides it in an elliptic integral, which unfortunately is the case for our new little buddy. Now we can look at the curvature, which tells us more about how the curve curves.
Every plane curve has its own unique curvature, up to translation. How much it wiggles, basically. The formula for curvature is the modulus of the determinant of the matrix formed by the tangent and the tangent's derivative, all divided by the speed cubed. For a unit speed curve, the curvature is simply the norm of the second derivative. This is how much our little fella wiggles.
Okay, right, so here we found a little space curve. He's quite nervous, so we have to be quite quiet. So this is the second kind of curve I was talking about. So we've got the plane curve, this is the space curve, and it gets its name from the fact that it's in 3D space, so it's a space curve. And a lot of the properties of the space curve are very similar to that of the plane curve. So we can see the speed of the parameterization, whether it's regular or not, in exactly the same way. So you take the curve's parameterization and you find you differentiate it and you find the magnitude of that. If that's equal to 0, then the curve is not regular. But otherwise it is regular, and if it's equal to 1, then it's a unit speed parameterization. And then to find out the length of a certain part of the curve, you would do exactly the same process. You would just integrate the parameterization, the magnitude of the differentiation of the parameterization between two parts on the curve, and then you would find the length of that little bit of curve, just exactly as you would in a plane curve. And then because of its 3D nature, not only do you have the curvature in the direction of the parameterization, you also have another curvature, which we'll call the torsion, which we'll explain in a little bit more detail in a second.
Looking at the curvature is very similar, but because of the extra dimension, we effectively have two curvatures to look at. Curvature is how much it curves in the direction of the motion, and the torsion is how much it curves perpendicular to the motion. In our case, we calculated the torsion to be 0.
A way to relate the two curves is that the 3D space curve can project onto 2D to make a plane curve. We've managed to find a 3D curve that projects onto our new friend, and from this we can show you its properties too. For this guy we can see the curvature, but it doesn't have a torsion. This is because a particular species of curve is fixed on a plane in 3D.
Hello. So I'm going to tell you about a couple of cool properties that I think that the little end of the surface has. So one of them being that it's something that's called a conjugate of itself. So if we have a look at these two surfaces, so we have a look at the white surface here, and then look at the blue surface here, these are actually exactly the same, just flipped and turned around, if you will, but these surfaces are exactly the same. So it is a conjugate of itself. And another cool fact is that this Oedipus surface is part of a family. This is an Oedipus surface of order 2. So it's got 2 curves going up and 2 curves going down. There is another famous example, the monkey saddle surface, which can be shown here. That's a surface that has, 4 curves going down and then 4 curves going up. So this is kind of like to allow for the monkey's little legs and the tail and his hands, and then to be sat comfortably and safe inside. Those are some cool properties about the Oedipus surface.
Every surface has 2 fundamental forms. Our surface's first fundamental form is now showing on screen, and the surface also has a second fundamental form as well.
The Oedipus surface has a mean curvature of 0. This means that it has the same amount of curvature anywhere along the surface, and this also means we can call this a minimal surface. The minimal surface has a curvature which we can also compute. Tying in the curves, we can measure a lot of properties of the surface by looking at how the space curves that run along the surface behave and what their properties are.
So, thank you for tuning in to this week's special of Maths in the Wild. So tune in next week. We've got a special guest coming in, Dr. Katrin Lesh. She'll be talking about her adventures in Mathsland. Till next week.